Hi, friends of the sun. Welcome to our reading group here, where every week we have a paper author who wrote a pretty cool paper coming here, explaining the paper to us and discussing it with us. And us is just anybody who wants to join. So can include you. If you want to join in the future, then all the information is down in the description. It's just a Zoom room that you can join. And we also have like mailing lists with the upcoming speakers and a Slack channel where you can, for example, suggest speakers for the next week. But yeah, today we have Nathan, who's talking about discrete walk-jump sampling, which is like a discrete diffusion model-like approach for generating sequences. And they do this for protein sequences, and it works quite well, it seems. So yeah, pretty interesting. Enjoy and see you next week.
Yeah, I've got a couple slides from an old workshop talk that is maybe a good broad intro. And then if people have questions or want to discuss anything, just stop me at any point, and we can go to the paper too. There's been yeah, that's title is outdated. So the paper is protein discovery with discrete walk-jump sampling. And we were just accepted as an oral presentation at ICLR for 2024. But before that, we presented this work as a spotlight at a bunch of different workshops. So this is like an old version of slides, an old version of the paper is on archive. The camera ready will be out soon. All the ideas, like all the content and the methodology is exactly the same as you might expect. The updated version just has additional benchmark experiments and stuff like that.
Additional benchmark experiments or also additional experimental results?
Yeah, so there are some updated in vitro experimental results as well. So there's both in silico and in vitro experiments updated in the camera ready. And I can also show that too, maybe just to highlight what the main points are. And I'll just maybe signal where in these slides things have been updated. Yeah, so I can just go ahead and give a kind of overview of the paper, if that makes sense.
Yeah, let's
Cool.
do that, and let's also try to keep the. I mean, sure, we can talk about connections between energy-based and score-based models, for example. But yeah, let's be sure that we've seen diffusion models many times.
Yes. Great. Okay, I'm just gonna skip over the background then and let people ask questions if they have any. I will just say, there are problems and difficulties with training and sampling from energy-based and score-based models. So that was the that was the motivation for this work. And like, lots of other work in diffusion and generative modeling, the basic idea is how do you smooth the probability density to make sampling tractable, efficient, get good sample quality. Okay, so I'm going to jump right into the details of discrete walk-jump sampling, and we'll just kind of go through this. So I'll say this in many different ways throughout the next couple slides, but the core idea of discrete walk-jump sampling is very, very simple. And a lot of, I think, usually when I go over this with people, the thing that makes it click easiest is just to think of it as like a single step diffusion. So if you think about a typical diffusion style model where you have a noise schedule and you kind of have to carefully tune that, and you're noising over all of these different noise scales, and that is generally one of the trickier things to tune during your training and sampling. Our main observation here for discrete data in particular, so in this paper we're always working with sequence data, protein sequence data in particular, but it could really be any kind of discrete sequence data. The observation is that you actually only need a single noise scale to achieve everything you want out of your diffusion model. And that basically all of those other noise scales that you're interpolating from the whatever distribution to your target distribution. Everything else is kind of superfluous, wasted compute, if you can find that one noise scale that you actually need. And so we do that with a method called neural empirical Bayes. And so the intuition, first we'll talk about this denoising or the score-based approach. And here it is exactly what you're very familiar with in any kind of score-based denoising formalism. So we train a score-based model on smooth data. In this case, the way that we smooth our data is we do it in the simplest way possible. So you could take, for instance, a one-hot encoding of a discrete sequence and add isotropic Gaussian noise to those one-hots. The one-hot encoding is kind of the simplest way to do this. And like a very natural way that you could also think of doing this is with a learned dense embedding, right? You could take like a pre-trained language model or something that comes up with a representation for your sequence, transforms your discrete sequence into something continuous. That works too, but it's just very simple and gives you very good results to just take the discrete representation and add noise to it. Yeah.
Okay. Yeah. So then the things that you've been saying so far about taking one noise scale and finding this with neural empirical, right? The neural empirical Bayes and the single noise scale stuff that you've been saying, that would also apply to continuous diffusion models, right? And
yeah, absolutely.
What of this is now making it especially nice for discrete?
Yeah, for discrete. Yep. Yeah, so I would say that this is really an observation. So this is really an empirical observation that when we try to apply this like neural empirical Bayes and the walk-jump formalism on continuous data, so like a very, I'm sure, familiar one to lots of people here would be something like 3D coordinates, right? So you could do a like conformer generation or structure sampling with this approach. And I think that's very interesting and promising direction. But there we just see empirically that it is much, much harder to train and sample with a single noise scale. There's something about the diffusion, like the continuous diffusion on continuous data, kind of like naturally continuous data, that works well. Similarly for guidance, so some people might be familiar, we have kind of a companion paper to this one called like guided discrete diffusion for protein design. And there the objective is not just to learn a probability density, not just to learn a data distribution and sample from it in an unguided way like we're doing here, but to use some kind of gradient guidance based on classifiers that you've trained to sample, in this case, protein sequences with optimized properties. And there also we see that kind of like the diffusion framework, being able to do iterative refinement is just very empirically useful for applying guidance and getting good results for guidance. You can do that here too. There's nothing stopping you from doing this on continuous data. There's nothing stopping you from applying gradient guidance to walk-jump sampling. It is more just like an empirical result that we've seen.
Okay, good. Then I think I have some more points and questions on that, but I think you can come back.
Okay. Yeah, we can keep
So
going.
Rafiki is back, Dom, just in case that's the person. And yeah, let's get back to that later. But now we're doing discrete, and you say for doing discrete, we just take our one hot vector and treat it as something continuous. We, so to say, have a Dirac delta, or our data distribution are different Diracs. Yeah, then we add noise to this until it converges to standard Gaussian. That's centered at 0.
Yep. Yes.
All
Yeah.
right.
Exactly. Yep. Exactly. So, right. So that is the setup. Then this kind of neat, this neat result from empirical Bayes and neural empirical Bayes tells you that if we choose our noising process to be isotropic Gaussian noise, then we know exactly how to recover or estimate what the clean data will be. So in our notation, Y is the noisy smooth data, X is clean data that you're training on, and then X hat is your estimator for clean data. So you get this very simple result where you just add back the score function and scale it by sigma squared, where sigma is the noise scale for your Gaussian noise. So this gives you back, this tells you how to denoise and recover back clean data. And it has this very, very simple form when you choose isotropic Gaussian noise. There is, you can definitely ask then, right? Like there are lots of other choices of corruption that you could do and that people do in diffusions or other contexts. Here, the Gaussian choice is again kind of motivated by simplicity and by having this very nice Bayes estimator. There have just not been this sort of result derived for other types of noise, but that's not to say that one, you couldn't derive a similar result like this for a different choice of noise. That's very possible. Just no one has done it yet. And two, it could also be the case, right, that empirically you could just choose other types of corruptions and that you would just see it work empirically. So I don't think there's anything, I mean, you can kind of apply lots of nice intuition and you can use this when you choose Gaussian noise, but I don't think that that is, you know, a very strict restriction. So, okay, so this is our Bayes estimator. And then of course we can parameterize this with the neural network. So that gives us the parametric form. So now G phi here is the score function. So this is the function that we're going to learn through a simple denoising loss, an L2 loss. So this is very simple setup for how we learn scores in the score function. So this is kind of one half or one component of discrete walk jump. And so that was kind of to give you more of the details. This is just to give you a mental picture for what's happening. Again, if you're familiar with diffusions, this is not going to be too surprising. Yeah, Hannes.
So, but like what you set up so far,
Yeah.
this function that you're training, it's basically like training a diffusion model, but only at a single noise scale.
Only at a single noise scale. Yep,
with
exactly.
that, we could not get a generative model that reproduces our training distribution, right?
If you just had that, no. Okay, so now there's a second piece, which is not just learning scores on a smooth manifold, but learning energies on a smooth manifold. So here, instead of training with a denoising objective, we're going to train with a contrastive divergence objective, as is typical for an EBM. And this is really like the piece that is unfamiliar to people, but is again quite simple once you understand what's happening. The energy-based model is trained completely separately from the score-based model. They don't interact at all. There's no like adversarial loss going on. They're completely decoupled. And the energy-based model is only ever seeing noisy data. So again, we're training this EBM with a contrastive divergence objective. And the goal of the EBM, right, is to learn this energy surface and be able to sample new noisy data. So it's only seeing Y. It's only seeing these noised samples. This is much slower, right, in training in general, because now we're actually doing Langevin MCMC during training time to generate samples and train with contrastive divergence, which you can't see now. But I prefer this to the other stuff that was going on. But kind of one thing that is really interesting about this is, so for an EBM, training on this like, you know, this not smooth manifold of discrete data is extremely brittle. It's very, very hard to train an EBM on that data, and it's very hard to get good samples from it to
I'm
learn
sorry,
that
I'm
training
sorry.
distribution.
I'm sorry.
Okay,
Okay.
I muted this person.
All right.
Reports submit done. Okay.
Okay. So right, if you train in this way, the denoising model is trained to denoise, and what you're going to ask it to do at sampling time is to denoise noisy samples into clean data, the thing you're actually trying to sample. And the EBM is trained to sample noisy samples. And what you're going to ask it to do at inference time is give you more noisy samples. So there's very nice trained sampling equivalence here. And like I said, both of these models, these networks are totally decoupled. They don't depend on each other in any way. And there's, again, no noise schedule. We're still just training both models at a single noise schedule. So then we put it all together. And what we have here is a typical Langevin MCMC setup. But now this is broken up into these two pieces. So there's the walk part and there's the jump part. So in the walk, we have, we're following the gradients of the energy function. So here now F is this energy-based model that we trained. And we can sample new noisy data, new Ys, by just walking this energy surface, by doing Langevin MCMC with the gradients of the EBM. You can add all of your favorite,
Sorry, I was zoomed out a little bit and distracted a little.
Yeah.
You have now this higher level or this smoothed out energy landscape.
Yes.
I'm sorry, why you didn't kick Bo Kwang? It was not very good of him. It was not very ladylike.
Martin, no. Yeah, maybe you can remove Martins and report him. Thanks. Yeah, so discrete walk-jump sampling, right? We have our smoothed out energy landscape and distribution defined, Boltzmann distribution defined by that. And now you say you do Langevin dynamics in that, Langevin MCMC. Do you then actually reject some steps?
Great question. Yes. So if you're doing Langevin MCMC with a typical energy-based model, so basically anything before this work, you would do rejection sampling, you might have a replay buffer. There's like all kinds of tricks that you might employ to, one, just get good samples, and two, get good mode mixing. So if you're doing kind of typical EBM sampling, you're just gonna be stuck wherever you start. And here, basically we do away with all of that stuff. You can add it back if you want to, but it's basically unnecessary because you are only trying to sample this nice smooth distribution now. So you can very quickly, you can add terms if you actually don't want to mode mix quickly and explore the distribution. But natively, that's what this sampling procedure is going to do. So one of the vast simplifications of the approach is that you throw away all of the typical MCMC tricks for doing sampling.
But wait a second, like that isn't the argument for why we mix modes, that we now have a smoother convolved distribution that we can easily sample. And it is not that we have to reject and do MCMC, like the rejecting and doing MCMC is just what we need to do for the process to be correct, right?
Sure, there's definitely like some maybe like guarantees or theoretical justification to do rejection sampling. But if your goal is just to ensure that you're not getting stuck in local minima, we don't have that problem here anyway.
So if we actually want to reproduce the training distribution here, right, then like in the infinitesimal limit, your equation, like your top equation, or the Langevin dynamics would be correct, and we wouldn't need to do any accept rejects, or
Yeah.
I just don't have wouldn't need some Metropolis Hastings
Right.
but now we discretize this, our
Mhm.
Langevin dynamics process, and that's we in principle to still sample the correct noisy distribution, we would need to have some Metropolis Hastings accept reject steps. But now what I was like these things are all clear to me, or maybe I'm also saying something wrong, and you can correct me. But what I was wondering is for our Metropolis Hastings acceptance criterion, where in the end, right, we care about sampling our, we care about sampling the what do you call this, the low energy or not the clean distribution. Yes, the clean distribution. Do we have to look at the density of our samples in the noisy distribution that they would have in the clean distribution, or do we just have to sample the noisy distribution and then at some point we push them to the clean distribution?
Exactly. We just sample the noisy distribution because that other model, the denoising model, is going to push them back to the clean distribution. So we never have to worry about when we're sampling from the noisy distribution, we're just generating noisy samples. And you can, at every Langevin step, you can take a new noisy sample if you want to, and push it back, or you can do that every k steps or whatever. It's totally flexible. And then the denoising model is what's doing what we call the jump step. So that is using the Bayes estimator to take the noisy data Y that you've sampled using the EBM, and you use the score-based model to denoise it back to, what we call X hat here, back to clean data.
Okay, this I think my question didn't really make that much, or it made sense, but it's clear, right, that if we have a function or we have a map that takes us from our noisy distribution to our clean distribution, and now we just need to sample the noisy distribution. Sure, we have here some error in what you're doing, and we're not sampling the noisy distribution. Yeah, we're not actually sampling the noise distribution, but it's fine. Practice it works. And yeah, so now one could also imagine doing something like training, right? We need an initial sample that we in your clean distribution to which we add noise, bring it into a noisy distribution, and then run our stuff. Have you thought about like, and then maybe it's still sometimes hard to switch to other modes. Have you thought about something like you now have your, okay, now what I'm saying is stupid. I want to propose you have your noisy distribution and then you train a diffusion model on that easy distribution. And then, yeah, and then you can easily sample this easy distribution and you have more diversity, so to say, in your samples. But yeah, I mean, then why not train the diffusion model the whole way? Yeah.
Yes. So you're right. So for initializing sampling, you can do it really any way you want. So if you have, say, again, for our like kind of application area here, if you're doing protein sequence design, you start with some sequence, wild type sequence that you're trying to design, and you add noise to it exactly as you described. Or maybe you add noise to only specific segments or chunks if you're doing infilling, right? So everything here is non-autoregressive, which is great because you can do arbitrary infills of any part of the sequence, and just resample wherever you want. You can also initialize sampling purely from noise. So you can just start exploring this distribution that you've learned by initializing stuff from noise wherever, and you'll just kind of, another cool thing, right, is you can do all this in a single MCMC chain. So you can initialize your noisy sample anywhere you want and just run long chain MCMC. And you will pick up all of the modes in your distribution. And you don't even have to wait that long. It'll be like you can easily do this in a couple hours for data sets with hundreds of thousands of samples or millions of samples versus like, again, in traditional MCMC, you'd never see something like that. Yeah, so that's really the overview of the method and how it works and what the components are, and how you train it. I think the rest in this deck and the camera ready are in silico and in vitro experimental results. So I'm not sure, I guess, just based on the kind of reading group format and people, if there's interest in that, or if it's more just methodological.
No, yeah. Reading group format is maybe whatever I care about.
Sure.
And I definitely care a lot about the results here a bit and discussing about when this works well, why this works.
Okay, perfect. Yeah. Let me tell you
caveats at you and you defending.
Yeah. Let me tell you where it works well and where it doesn't work well, because this is also opportunities for future stuff. So yeah, so basically, one kind of not trivial result for protein design is to either, like we described, start from a sequence that has some function and then redesign parts of it and hopefully get improved function, or to start sampling from pure noise, and generate brand new protein sequences that have very low sequence similarity to anything in your training data, and then have those actually be expressible in the lab. So you create a sequence, it's maybe 80 to 90 Levenstein edit distance away from anything in your training data. You could do that very easily with walk-jump sampling, and then basically 97 to 99% of those designs are going to successfully express in the lab. So we're almost always working with antibodies, because that's what we're at Genentech, and that's one of the main things that Genentech is interested in. So what that means is that all of these designs coming out of this model, they fold into the kind of canonical antibody fold, and the expression systems that produce our other therapeutic antibodies can produce the designs from this model as well. So I guess to give you a sense, it is possible to break expression with a single mutation to a sequence that expresses already. So you could insert or delete a residue, or just change a residue from some chemical composition to another one, and you can completely break expression. Sometimes you will pick that up if you look at like a log likelihood from an autoregressive model or something. So you might see that the likelihood of your sequence has just dipped because you've done something very catastrophic to the chemistry with your local mutation. But that's just to give you a sense that like many ML models that produce sequences do not express in the lab when you actually try to make those proteins. This is
So what did you actually train here? Did you your diffusion model conditioned on the epitope or something here? Or did you just train a model on all antibody sequences, and then you now have a local, maybe already kind of good antibody, and then you get some diverse samples around it?
Yeah, absolutely. So we've basically done all of the above. So in some cases, we just train on kind of like the entire universe of public antibodies and create new ones. In some cases, we train on antibodies that are only measured or predicted to bind to a particular epitope on a particular target. So we can kind of implicitly condition on an epitope or just on a broader target that way. So that's kind of what we're showing here on this side. There's this antigen target called HER2, which is very popular for these sort of in vitro benchmark experiments, because there are already lots of drugs out for HER2, and it's something that companies like us are happy to talk about and share things about. And so again, this is an old in silico result where we're predicting binding to this target. The newer experimental result that we have in the paper is that when we actually tested this in the lab, Walk-Jump generated around 70% binders to this target. So what that means is we're training on binders to the target, we're sampling from that learned distribution. We enforce that all of our designs are, at least one edit away from something in the training distribution, but the mode is more like 5 or 6 edits away. We're always redesigning a very particular chunk of the antibody here, which is generally one of or the most important piece for binding. And then we benchmark this against a bunch of stuff: diffusion models, mass language models, autoregressive models, including GPT-4, which I'm happy to talk about because that's kind of a fun experiment that is, it's in the paper, but it's not the focus for most people, although it is fun to see the results. Yeah.
So what are you actually then evaluating here?
Yeah.
Are you just checking when you say you benchmark this against or blah?
Yeah.
You mean that you check the number of sequences that were expressed? Do you check the number of sequences that bind? Do you check the number of sequences that bind stronger than the wild type?
Yeah, express and bind. Binding stronger than the wild type is not a great evaluation in this particular case, just because the wild type here is a drug, is a therapeutic antibody. So if you see, so this is for a very specific antibody called trastuzumab on HER2. And I guess just as an aside, if you ever see results that claim to have stronger binding than that antibody, it's possible, right? It's definitely possible, like with noise in the experiment and variation, that you might see that. It's extremely unlikely that you've generated something that is like a better drug than trastuzumab. So we don't really care so much for this example about improving binding. Instead, what we care about is sequence diversification. So we want to generate new designs that are meaningfully different from the wild type, but that retain binding. So for Walk-Jump, that means 70% in vitro binding. For diffusion models, we've tried like structure-based diffusion models. That's more like 20%. And for our guided diffusion methods, it's around 30%. So that gives you a sense for like where these things clock in. Now, you can definitely improve any of those other models by doing some kind of selection, right? Here, we are just training on this distribution of known binders and sampling from the model and testing a random subset of those. We don't do any kind of, we don't use like an external classifier or anything else. So of course, as long as your model is able to produce binders and you have a way to pick them, that's the tricky part, right? Usually you don't have a good way to pick them. Yeah, but you could of course improve those other methods. So this is more of like a, if you just do sampling from all of these models and you don't intervene in any other way, what percentage of binders will you get from each of them? And then for GPT, unfortunately, I didn't have the budget to do an in vitro evaluation for GPT. So instead, we trained a pretty performant classifier. There's enough data for this particular binding interface that we can do pretty well at classifying. And so we just predict the number of GPT designs that will express and bind.
Yeah, so on that point, we already have now say we have enough data. Diego is asking, what is the exact data that you train the generative models for the HER2 case?
Yes. Yeah. So in this very general case, there's something called observed antibody space, which is a lot of antibody sequences from Genentech and other companies and lots of academic groups, which is just like all of the antibody data that's ever been deposited publicly. And then for this case, there is a paper by Cy Reddy's group from 2021, I think, a Nature Biotech paper where they do what's called deep mutational scanning. So they take this wild type antibody and then they introduce a bunch of mutations at the at where they think the interface is. And so we trained on that data. So that,
Okay.
yeah.
And did you look at something like diversity metrics as well for
Yeah.
the generative?
Yep. Yeah, absolutely. So diversity metrics here are quite easy because in this data set that we trained on, they're only making mutations to what's called the CDRH3 region. So it's 10 residues for this antibody. So that gives you 20 to the 10 possibilities of your designs if you consider canonical amino acids. And so diversity here is just a very simple edit distance metric. Basically, if you are creating something novel with mutations that don't exist in the training set, you can score diversity by increasing the edit distance from the training samples. But that's actually a pretty informative metric here.
Okay. And then how do the different generative models compare there? Because an essential difference of the like you did not, I think of the methods that you just mentioned, you did not compare to anyone that also is local and starts out with a seed, so to say. And
So
this
they
only
all start out with seeds in the sense that they're all initialized from the wild type antibody. So for every method, we're doing infilling on this particular region and conditioning on everything else. With the exception of GPT, where I'm basically, the way I did the GPT experiment is with, I guess, in context learning. So basically trying to coax GPT into producing these CDR-H3 infill designs by just giving it, a couple examples until it was able to do the task. So
okay.
GPT is not conditioned on the rest of the antibody.
So what you said is like you're conditioned on the rest of the antibody, you're also conditioned on the epitope?
So your one of the structural diffusion method is explicitly conditioned on the epitope because it's a cogeneration method. It's generating both the antibody sequence and the structure. So it's explicitly conditioned on the epitope. The other methods are.
Oh, hello. Can someone confirm to me whether it's me or Nathan? Can you
It
guys
was
hear me?
Nathan.
Okay. And maybe for Ingrid, while Nathan is maybe trying to rejoin, but isn't here yet. So far, right, we haven't talked about anything about optimization, and we're just generating sequences, and we're not trying to guide toward a certain property or to target a certain like some tilted distribution that's been tilted with a value function or something like that. And yeah, I'll also ask him about whether we can target some properties, like for example in the protein discovery with the skewed discrete diffusion paper, right there they targeted multiple objective functions at once and tried to do that. And I'm also going to ask him.
Hey, sorry, just
yeah.
lost my connection there, but I'm back.
Yeah, we were just talking about a question of Ingrid regarding guidance, I guess a little bit, but let's get to that later. I think there are quite some points regarding that. But here now you mentioned you have your antibody and sure, so the models are all conditioned on the rest of the antibody. So GPT is and some are also conditioned on the epitope. But what I mean with from a starting point is, right, we're trying to design the CDR. The CDR is the space in which our distribution is defined. And your walk-jump sampling, I assume, starts with the wild type sequence, and then you add noise to the wild type, and then you start from this local thing.
Mm.
And now you could also imagine doing GIPs with gradients or discrete MCMC methods around
Yep.
that with that sequence as starting point. And do you also compare against something like that?
Yeah, that's a good question. So actually, we do the inverse. So we start sampling from noise for walk jump, not from the wild type. The structural diffusion method starts from the wild type,
Wait,
and so
wait a
does
second.
guided
Are
discrete
you
sample. Yeah.
are you saying you sample from a Gaussian, standard Gaussian, and then you
Yes.
run the Langevin dynamics?
Yes. Yep.
Okay.
Yeah, exactly. Yeah, you absolutely could start from the wild type if you wanted to, and that would be just a good way if you wanted to constrain that mutational distance and you wanted to retain most of the wild type sequence, you could
By the way,
absolutely do that too.
how many steps of Langevin dynamics do you run?
So we do CD20 during training, and we generally try to match that at sampling as well, like 20 steps. So thanks for bringing that up too. So that's another thing. Again, people who like haven't really messed around with EBMs because they've been unfashionable for a while might not, that number will be very surprising to you if you've tried to train EBMs before. Typically, because you're doing Langevin during training, you'll do very, very small number of steps because it's so slow. But we do kind of like, in a sense, long chain MCMC, both at training and sampling time because it's very fast.
Okay. Then what else did I want to ask on that side before we skip around somewhere else?
Yeah.
Right. Diversity metrics. I think you
Yeah.
mentioned some diversity metrics and the relevance of them, but how do the methods now compare for diversity?
Yes. Yeah. So there, honestly, we don't see a ton of difference. I think basically all methods are capable of, well, so I should say it differently, right? So the trade-off is going to be exploration, exploitation, right? You see this all over the place. The trade-off is going to be diversity versus you retaining function, like retaining binding, right? So basically all the methods you can sample in such a way that their diversity metrics will look good. You can just at sample time, you can control that. The difference is that if you try to match the diversity statistics of walk jump, function is going to go way down. You're just going to start going into unlikely regions of sequence space. Oh, actually, and I'll say again, that is the main failure mode of GPT from what I saw. It really struggles with redundancy. So I think they're like, I don't know, if you're a prompt engineer, which I'm not, I'm sure there are ways around this to like, I don't know, to increase diversity or get away from the redundancy problem. But all of these diffusion-based or walk-jump methods can generate, right, thousands or tens of thousands of unique sequences very easily. So yeah, that's a challenge for autoregressive methods.
Okay. Then you have this line up here: extrinsic fitness equals function
Yeah.
equals max objective value.
Yes.
What did you want to say about that?
Yeah. So I took this kind of explanation from Brian He's paper in 2022, where he kind of explains generative modeling for proteins in this way, and that there's, for a length L sequence, you have 20 to the L possible proteins that you could design, which is this full mutational space. There is a much smaller subspace of what are called highly intrinsically fit proteins. So you could think of that like high likelihood sequences that you actually observe biologically and that will fold into something with secondary structure, but maybe not necessarily have function, but will fold. So, if you're in this mutational space, which a lot of generative models are, you'll generate, it's a strict vocab. It's very easy to generate any protein sequence is a big difference between this and small molecules, right? If you just randomly sample SMILES tokens, you're just going to get some garbage thing that doesn't actually decode into a valid molecule. You can fix that with your vocabulary, but again, you might sample stuff that just isn't even chemically plausible or accessible. In protein space, you actually can do that too. People, it's the point maybe isn't as well understood, but in proteins, if you just randomly sample or you sample from a bad generative model, you will just get junk sequences that either one, you can't actually synthesize the DNA, so you can't create them anyway. And even if you did, they won't get, this nice, secondary structure, which can give you function and other sorts of stuff. So high intrinsic fitness means you're sampling high likelihood things. That is what we see with expression and folding. High extrinsic fitness is some kind of function that you're actually trying to get. So in this case, one of the simpler ones, which is still very complicated, is binding. So you're trying to design a protein that binds against another protein. And so this is an even much, much, much smaller subspace where having high extrinsic high extrinsic fitness gives you function. That's what you're trying to maximize. And this kind of segues into a really nice point about what walk-jump can't do, right? So in this situation, I have a bunch of this mutation data that gives me examples of things that bind at this interface. So there's a lot of information about interventions and perturbations. You can almost think of it causally, like if I make this chemical change at the interface, physicochemical change, is it going to retain binding or break binding? And so we have this very nice distribution that we can sample from with walk-jump. If you are, to Hannes's earlier question, trying to explicitly improve binding compared to wild type, or you only want to generate binders and you have very few binders to look at, walk-jump in this setup is not configured to do that. There is no guidance happening anywhere here. You're just doing unguided. You can do conditional sampling, but it's unguided. There's no gradient guidance happening here. So yeah, that is something that we've taken different approaches for. We have tried to do classifier guidance for walk-jump.
How would that work?
Yeah, so you can actually just add, so this is just in EBM here, right? So you can add anything to your EBM that you want. You can add anything, any other energy terms, any other terms that you want here at the Langevin step.
So in
or here, you can actually do it either way. You can do it during sampling of noisy data, or you can try to do it at the jump step. So you're denoising from noisy data to clean data along with following some additional gradient information that tries to snap you back to a part of the distribution with improved function. You could try either way.
I don't quite see how you could do it in the second way, like at the denoising step. That seems to me like then you would need to run multiple steps of denoising.
Yeah. So practically speaking, this is where you get the trade-off, I think, the disadvantage, right? In a diffusion, when you're doing this kind of like, iterative sequential denoising, you have many opportunities to update the sequence, right? If you're doing gradient guidance, you maybe diffuse a token somewhere in the sequence, and 5 steps later, you've resolved some other part of the sequence and there's some incompatibility there, right? Or something you've introduced some interaction that's unfavorable, but you keep going, right? You keep diffusing so you can resolve that, and you can do this iteratively. In walk-jump, you could imagine doing that with this long walk chain, right? Where you might do many either guided jumps or many guided walks followed by just denoising jumps. And you might say that, like, okay, for my guidance objective, 99 of these sequences are junk. They just they don't actually maximize the objective, or I messed up the likelihood of the sequence or whatever, right? So you could do like you could still do something like iterative refinement and guidance here, but to be honest, it's not as natural to me as I think in a guided diffusion. It's
Yeah,
not to
but
say it's not possible, but yeah.
I mean, if we do multiple steps of denoising from our noisy to our clean distribution, then sure, there we can also do guidance. And we can also now like tilt our no, we cannot. It would also, I think it wouldn't be correct to tilt the high, the noisy distribution to sample it, right? Because then
Yeah.
your diffusion model isn't trained on that distribution. So I think
Yes. Yeah.
it can't like easily be guided. Yeah.
Yes, exactly. Yes. Yep. Yeah, exactly. That is exactly the problem we see trying to tilt the distribution, because exactly. You're trying to then sample something that is not the training distribution.
Okay. Then let's also be cognizant of your time. How much longer can we have you here?
Yeah, I unfortunately only got 5 more minutes. I gotta leave at 12.
Then let's maybe get to some higher level questions.
Yeah.
Did you try this for text data?
Great question. Yeah. So there is this text 8 data set, which is something like, I don't know, a big chunk of Wikipedia. And so we've done some experiments on that, just because it is, you just, swap out the vocabulary in the data loader and everything works exactly the same. So yeah, it's great for text 8, which is like a playground for NLP models. But we haven't tried it, I don't know, in like kind of production NLP settings, or like the sort of data sets that people would report in NLP papers.
And did you try it for images?
Yeah, well, so a kind of neural empirical Bayes was actually tried on images first, like before we introduced the EBM formalism and the approach to discrete data. Just this score-based approach here, and with the empirical Bayes estimator, was tried on images, and it works. It is, I think, getting to the problem that I mentioned right at the beginning with, more natively continuous data there, when you're dealing with pixels and pixel values. It works, but it is very difficult to outperform a typical diffusion, an image diffusion.
Yeah. Okay, so I kind of wonder a little bit. So I think one of the strengths that we could have here with walk-jump sampling is this possibility to sort of stay local, but in many of the experiments, or in some experiments, apparently you even do not start with an initial seed. But I also wonder a little bit if the reason why this performs well for protein generation compared to the other protein generation methods is just because our protein language models are actually pretty bad, and all of our sampling methods are quite bad. And I've played around with like discrete diffusion models and so on, and things for sequence protein sequence generation, and like some compute in terms of computational evaluation metrics, they all were pretty bad. Like taking ESM, finding it as a diffusion model, taking prod GPT and things like that.
Yep. Yes. Yeah, I totally agree with you. And we've done similar experiments here, and I think that is partly just, those bad protein language models, partly because at the time most of those were developed, there was either very little or no consideration put towards thinking about inverting those models or using them for anything other than just kind of representation learning purpose. I guess, I mean, with ProGPT exception, which is specifically for autoregressive generation, which also I think is just not not a great approach for proteins in general.
Okay, interesting to hear that this is maybe not just something I'm imagining, and
Yeah.
I think that's maybe a good concluding remark, unless
Yeah,
you want
absolutely.
to say something.
I will show just this to finish up in case anybody wants to get in touch with me. If you have more questions or you just want to talk or whatever, feel free to send me an email. And then I always like to make a special thanks to my co-authors, Dan Berenberg and Said Saremi, who did the work with me.